Hello everyone, Jai Hind. So I'm going to discuss regular expressions and its equivalence, that how regular expression is going to be equivalent to finite automata, and finite automata is equivalent to regular expression. And I'm going to discuss equivalency of regular expression with uh, regular grammar also. So this is outline of the content. I'm going to define the regular expressions first, that what is regular expression and what are its applications, and then next one is equivalence to finite automata, how regular expression can be converted into finite automata, and finite automata can be converted into regular expressions. And next topic is equivalence to regular grammar, how regular grammar can be converted into regular expression and vice versa. So as we know that regular expressions are convenient notations to describe the regular set. So what is regular set? Any set is called regular if it is accepted by some deterministic finite automata, right? Suppose I'm having a set, let's say A comma B comma C. So this set is going to be regular because we can design a finite automata which can accept this this set, like say A comma B comma C, and we can say that this is the finite automata which can accept. So therefore this set is going to be a regular set. So if a set is not going to be accepted by any finite automata, it is going to be categorized as non-regular set. So what is regular expression? As I said, that it is a convenient notation to describe regular set, or we can say that this is an algebraic way to describe some languages. So this regular expression exactly they describe exactly the regular languages. What is regular language? Any language which is accepted by the finite automata. So if E is regular expression, then L is the language it defines. It is very easy that if I am saying that if E is any regular expression, then its corresponding language is LE. So I'm going to describe regular expressions recursively. So if we are defining any regular expression recursively, so first one we are defining the basis of the inductions, like basis of the regular expression. So there are three things. First one, we will start with phi, and next set is empty set, and then A belong to any sigma. So these are the basis of the induction, right? So you see here, if phi is a regular expression, then corresponding language is phi. If epsilon is a regular expression, then corresponding language is epsilon empty. On the other hand, if A is any symbol of this any alphabet, then A is a regular expression and corresponding language is A. So this is base of the induction. So okay, so what is next one? How to proceed with induction? Induction one is saying, if E1 and E2 are regular expression, then E1 plus E2 is a regular expression and corresponding language is L. E1 plus E2 is union of E1 and E2. Like say, for example, A is regular expression by rule number 1, this basis number 1. And B is also regular expression by the same basis, basis number 1. So this rule induction 1 is saying that if A is regular expression and B is regular expression, so definitely A plus B will be regular expression. And what is its corresponding language? LA union LB. So what is LA? LA is A and LB is B. So actually this regular expression is representing A comma B. So it is very simple that so it is representing A comma B. What is union induction 2? If E1 and E2 are regular expressions, then E1, E2 is also regular expression and its language is E1, E2 is LE1 concatenated with LE2. For example, 0 bar is regular expression by this basis A, and 1 bar is regular expression by the same basis. So that means 0 bar dot 1 is also regular expression by this induction 2. So if we just like conclude this induction 1 and induction 2, 0 bar is regular expression, 1 bar is regular expression. So 0 bar plus 1 bar is also regular expression, right? So yes, and second one, induction 2, if 0 is regular expression and 1 is also regular expression, then dot is also regular expression. So concatenation is just like concatenating one after other. So induction number 3 is saying that if E is regular expression, then E star is also regular expression. What is E star? E star is clean closure, right? So for example, if 0 is regular expression, so then 0 star is also regular expression by induction number 3. So this is very easy. This star, as we know that this 0 star is what? Epsilon plus 0 is square plus and so on. This is clean closure of 0. So this is actually induction number 3. So what is next after this induction? So any regular expression, any expression is going to be regular expression if it is made by the basis and induction 1, 2 and 3. So generally, let's see, if I'm saying another rule is saying that if E is regular expression, then parenthesis E is also regular expression, right? So if you are saying that E like see 0 plus 1 is regular expression, so definitely their parenthesization of 0 plus 1 is also regular expression. So we can say that this is induction, this is like rule number 4. Rule number 4, right? If E is regular expression, then parenthesization of E is also regular expression. So by this rule, if we can say that 0 plus 1 is regular expression by induction 1, so definitely 0 plus 1 star will be regular expression because of induction number 3. So, but what about this 0 plus 1 dot 1? Is it regular expression? Answer is no, because there is confusion that 1 dot 1 are 0 plus 1. So if we define this, this is clear cut that yes, this is regular expression, because if 0 plus 1 is regular expression, then its parenthesization is also a regular expression, and we can concatenate them, so it become regular expression. Again, if you want to make it star, it is also regular expression. But on the other hand, if you just define 0 plus 1 dot 1 and like this and making star, this will not be a regular expression because there is confusion that this star is on A or it is on complete 1. So if we define this, ambiguity will be removed. So this is the regular expression definition. So there is a remark on this operation, like operators plus dot and star, they are known as regular operator. We have only 3 operator, plus, dot and star. We call them regular operator. So parenthesis may be used whenever needed, as I just discussed. So order of precedence, when you remove the parenthesis is star, then concatenation, then plus. Like see, if I am saying that 0 plus 1 dot 1 is star, so what is order of parenthesization? This will be taking first, then this is the second, followed by this. This is the parenthesization order. So this is enjoying highest priority, and then followed by dot, then followed by plus. So see, like here, language 0 and 1 is like 0, 1. Language of 0, 1 plus 0 is 0, 1, comma 0. Same thing 0, 1 plus 0, concatenation 0, 1, 0. So this is actually the language and corresponding set. Remember, if you are defining any regular expression, there must be a corresponding set. You cannot define regular expression without defining the set, right? So same thing here, language of 0 star is going to be this. So next is how to convert regular expressions to finite automata. So we have many methods. First one is like Thomson construction. This is very old method. Thomson constructions. Thomson's construction. Thomson construction to convert regular expression to finite automata. In this construction, generally we are not getting DFA or we are not getting NFA, we are getting NFA with epsilon mu. This Thomson construction from regular expression to finite automata is generating NFA with epsilon mu. So let's understand this, like we need to show that for every regular expression, there is an automaton that accepts the same language. Regular expression to NFA with epsilon. In this one, pick the most powerful automaton type, which is the NFA with epsilon mu. This is the most powerful finite automata. And if you are converting finite automata to regular expression, if finite automata to regular expression, generally most restrictive type we are choosing is DFA. So DFA to regular expression is the reverse order. This is the most restrictive type of finite automata. So let's understand how converting a regular expression to NFA with epsilon transitions. As you know, we know that there are three regular operators, right? Plus, dot and star. So, and any regular expression is made of all these three operators, plus, dot and star. So let's deal with them individually. That okay, if R1 is regular expression and R2 is regular expression, so how to make finite automata for R1 plus R2 and how to make finite automata for R1 dot R2, and then how to make finite automata for R1 star. We know that star is unary operator, right? So this is actually, if we understand that how to convert regular R1 plus R2 to finite automata, R1 dot R2 to finite automata, and R1 star to finite automata, we can solve our problem. Okay. So this will be the block diagram. We are going to discuss using the block diagram form of NFA with epsilon. So you know that this diagram is already showing some machine, individual machine. If you want to add some state, it will be added explicitly. So this machine is already built. We are not going to build this machine. So yeah, like see. So let's start with the basis of the induction. Suppose we have symbol A. So what is its finite automata? This is A. You remember, you start with Q0 and this is the final state. Let's say this is this. And now this is actually accepting A, right? So this we are done with the basis of induction. Same thing here. If we start here, epsilon, Q0 and this is Q final. Now this is accepting epsilon. So there is another way to accept the epsilon. You can just make starting state and final state the same thing. This is also accepting the final epsilon. This is also accepting the final accept epsilon. So we can go by this way, or we can just make a starting and state as a final state. So this will automatically accept the epsilon. Here it is just like isolated, like here Q0 and it is starting and this is QF, this is final. There is no interconnection. So this language, this automaton is not accepting any language, right? So this is basis of the induction. So let's talk about, after discussing basis, we will talk about union and we will talk about dot and we will talk about star closure. So it's very simple. Suppose this is machine for, let's say, if we are talking about E1 union E2, we assume that there is machine for E1 and there is machine for E2, right? So this, suppose this is a machine where there is one starting state and another final state. So there is another machine, let's say this is starting of this machine and this is final of this machine. So in this of E1 union E2, what we will write, this is for machine E1, this is actually machine for E1 and this is machine for E2, right? So in union, what you will do, you will add another starting state, this final state which is not present in other state. Make epsilon go here and make epsilon go here. Same thing from epsilon go here and epsilon go here. So if you are following this way, you will accept language of E1, and if you follow the down one, you will accept the language of E2. So that means this is accepting language of E1 union language of E2, right? So this is very, very simple. So let's have one example. Suppose we want to make a machine for 0 plus 1, right? So it's how to construct a machine. We will construct a machine for 0 and here is machine for 0. This is accepting 0, right? And this is another machine which is accepting the 1, right? Yes. So if you want to accept 0 plus 1, this is regular expression. So it is very easy to make it final starting state. Go by epsilon over here, epsilon over here, and epsilon over here, and epsilon over here. Finally, make it this starting state Q1, Q2, Q3, Q4, and this is your final state. So look at here. If you go by this way, follow this way, epsilon 0, epsilon, it is accepting 0. If you follow this way, it is accepting 1. So this is simple one, that this entire machine can accept 0 plus 1 regular expression, or we can say that this is accepting 0 comma 1 set. It's very, very simple. Remember that this plus is unary operator. Yes. So on the other hand, let's talk about concatenation. So in concatenation, if you have two machines like C, so this is machine for 1 and this is machine for 2, right? This is machine for 1 and this is machine for 2. Second regular expression or second language, right? So in this one, this is starting state. Let's say this is starting state. This is final state of first automata. This is starting state, and let's say QF1, and let's say this is QF2 of the second finite automata. You know, this machine has multiple transitions. We assume that this machine has a multiple transitions, right? In this concatenation, actually from final state of first finite automata to second starting of second, we just write an epsilon move. Only one transition is required, additional transition. And finally, this is the final and this will be the intermediate. So this is the final state. This is not final and this will be the final starting state. So now this is accepting, suppose this is accepting LE1, right? And this is accepting LE2. So actually this will accept LE1, epsilon, right, and LE2. Okay, so actually this is accepting epsilon is just same thing. So this is accepting E1 dot E2. For example, suppose we are interested in 0.1. So it's very simple. Make a machine for 0, make a machine for 1. So if you just make a machine for 0, this is 0, right, and make a machine, write in the one after another, don't write in parallel, right? So this is 1 and you make it epsilon, right? So you see, finally this is starting state and this will become the final state. So this will accept 0 epsilon 1. So this is accepting 0.1. Actually, this is very simple concatenation. No additional states are needed over here. So next one is star closure, is like very easy. So suppose in star closure, this is your machine Q1, and let's say this is final state of the first one, and this is your finite automata. Okay, so if this is the finite automata, this will starting state, this is final state. So what will happen in this? You just add an additional state here, additional state over here, which is final starting state. And from this state, final state, move 1 epsilon here, from here to 1 epsilon, 4 transition, and from here to epsilon. This is final state from here to epsilon. So this will actually accept E star. E star means epsilon. Yes, by going from here to here, it will accept epsilon. You want to repeat it, you can repeat it by this way. There is no problem. You don't want to repeat it, go by this way. For example, consider the machine for 0 plus 1 star. Suppose I am asking to draw a machine for 0 plus 1 star. It's very easy. How to draw a machine? First draw the machine for 0 plus 1. So you go here, this is 0, and you go here, this is 1, right? This is 1, this is 0. Now if you just go by here, epsilon, and this is epsilon, right, and this is epsilon. Actually, this is accepting 0 plus 1. You want to make a repetition. In making repetition, add 2 states, one here and another here. Okay, so here just okay, add 1 state over here. So this is starting state and this is final. Rule is very simple. From here to here, make epsilon, right? And from starting to here, final state, make epsilon here. And from here, original final to make epsilon here. And from here to here, make epsilon here. So this will be the machine for 0 plus 1 star, right? Yeah. So all the machines can be combined together. Like see, construct a finite automata for 0 plus 1 star 0 1. So it's very simple. We can make the machine for 0 plus 1, right? So let's say let's make machine for 0 plus 1. Right, so 0 plus 1, this is 0 and this is 1, right? So this is 0, this is 1. 0 plus 1 is very simple to build, right? So this is epsilon, and now this is epsilon and this is epsilon. So this is machine for 0 plus 1. You want to repeat it, no problem. In order to repeat, you have to add 2 additional state. Here is epsilon and here is epsilon, right? And here is epsilon, and 3 epsilon we have already added. 1 more epsilon to repeat it, right? So this is actually 0 plus 1 star. After making 0 plus 1 star, this dot is hidden. You have to write for 0. So just write for 0. So this is 0 and connect them by epsilon, right? So this is 0. Again there is 1. So make like another machine for 1. Make machine for 1 and connect this by epsilon. So and this is finishing. This is the final state. And finally, this is the starting state. So this is very simple to develop the finite like NFA for any regular expression. Only drawback of this kind of NFA is that this has so many epsilon move actually. So if you want to convert this NFA to DFA, it is very difficult, like a very cumbersome task, that you have to go from NFA epsilon to NFA and then remove NFA and then converting DFA. So actually this is a tedious task because you have many epsilon moves. So there is like if question is asked that construct a finite automata, you can go with this, there is no problem. But if question is asked that construct a deterministic finite automata, try to avoid this system, because constructing DFA will require you to remove the epsilon, so many epsilon transitions. So there is shortcut method to construct a finite automata from the regular expression. So this is, we call it alternative methods, right? So construct a finite automata for this regular expression. So it's very simple how to construct, just like see here, start looking at the first one. This is 0 plus 1. So 0 plus 1 stand for 0 or 1. And star is here, so don't change the state. Anywhere if it is star, there is no need to change the state. It will be pumped over there, right? Yeah, so it is pumped over there. So we are done with this. And after then there is 0. So go with 0, right? And then again go with 1, right? So this is go with 1 and we are finishing here. So this is Q0, this is Q1, this is Q2 actually. So what is happening now? So this is NFA. 0 you are going to Q0 and 0 you are going to Q1. So that means this is NFA. This is NFA. So you want to convert into DFA, you have to write NFA to DFA construction. So question, if it is asked to convert DFA, find out DFA, is better to draw the regular, find the regular expression and draw the NFA with a NFA, and from that NFA convert into DFA. So you will get the corresponding DFA, right? So that this method is more secure, you will not commit the mistake, right? For example, suppose another question like see 0 plus 1 is star, and let's say 0 0 plus 1 1, and then again 0 plus 1 is star, right? So what is corresponding finite automata? Yeah, so here is you are not changing state, 0 plus 1 is star, we are not changing the state, and then this is the one, right? So go here 0 and concatenation, then 0 again, go here, right? And then again by 1, go here and again by 1. So 0 0 or 1 1. And again after reaching here, we are not changing the state. So this is 0 and 1. Actually here will be 0 and 1. So this is actually alternative method to construct the finite automata from regular expression. This is preferred when you are asked to find out the corresponding DFA. So these are the references. This is very basic book, John Hopcroft and Ullman, Introduction to Automata Theory and Language and Computation. This is basic book. Second is like KLP Misra and Chandrasekharan, you can follow this. And third one is the Peter Lynch, An Introduction to Formal Language and Automata. So thank you for watching.